ஷார்ப்பா 11 மணிக்கு ஆரம்பிச்சிரு ஜெயசிந்தியா.
ஓகே சார், ஓகே சார்.
ஷார்ப்பா ஆரம்பிச்சிரும். ஒரு 2 மினிட்ஸ் இருக்கு, அலோவ் பண்ண ஆரம்பிச்சிட்டு கரெக்டா 11 மணிக்கு அதை ஸ்டார்ட் பண்ணிடுவோம்.
ஓகே சார்.
சிந்தியா மேம்
சொல்லுங்க சார்.
மேம் உமா மேம் வந்து அவங்க நேம்ல வருவாங்க, இல்லைன்னா அவங்க ஹஸ்பண்ட் நேம்ல வருவாங்க போல.
ஓ ஓ.
அவங்க ட்ரை பண்ணிட்டே இருக்காங்க, இன்னும் அட்மிட் ஆகல சார்.
அப்படியா?
ஆமா, சார் பேர் ஆனந்த்னு வரும்.
ஓகே சார்.
சரி
சார், ஆனந்த் சார்
எது வருதுன்னு பார்த்துட்டு
சிலம்பரசன் சார்.
உமா மேடம் வந்து ஆனந்த் நேம்ல வந்தவங்க, அதனால அது வந்து அட்மிட் கொடுத்துறேன்.
சுபாஷ் இப்ப கொஞ்சம் குமார் பேச ஆரம்பிச்ச பிறகு நீ வந்துட்டு கோ ஹோஸ்ட்ல அலோவ் பண்ணு. என்ன?
சரி சார், இப்ப எல்லாரும் அட்மிட் பண்ணிடலாமா?
நீ 10:55 ஆயிடுச்சுல, அட்மிட் பண்ணிடுவோமா? என்னப்பா? ஓகே,
பண்ணிடலாம் சார், பண்ணிடலாம் சார்.
பண்ணிடுங்க.
மேடம்
சுபாஷ் சார்
அட்மிட் கொடுத்துட்டீங்களா?
நான் கொடுக்கல சார். கொடுக்கவா?
கொடுத்துருங்க.
நீ
ரூம் வருது, நீங்க கொடுத்துறீங்களா?
சுபாஷ் நீ தான் கண்ட்ரோல் பண்ணு. சுபாஷ்
இல்ல சார், கொடுத்துருங்க சார்.
நீ அலோவ் பண்ணு. அவர் டைம் இருக்கு, நீ அலோவ் பண்ணு. ஆளுக்கு மாத்த வேண்டாம்.
சுபாஷ் சார் அட்மிட் கொடுக்குறீங்களா?
மேம் அட்மிட் ஆயிட்டு இருக்காங்க.
அட்மிட் கொடுத்துட்டேன் மேடம். ஒரு தடவை அட்மிட் ஆகிட்டு இருக்காங்க மேடம்.
சார் சுபாஷ் சார் எனக்கு கோஹோஸ்ட் கொடுத்துருங்களா, நான் அட்மிட் பண்றது ஈஸியா இருக்கும்.
கொடுத்துறேன் சார்.
ஓகே சார். ஓகே சார். யூடியூப்ல நீங்க தான் லிங்க் போட முடியுமா, இல்ல நானும் போடலாமா கோஹோஸ்ட்?
இங்க என்ன சார் போட முடியும்?
ஓகே சார்.
சுபாஷ் சார், நான் உங்களுக்கு லிங்க் அனுப்பி இருக்கிறேன், நீங்க யூடியூப்ல போஸ்ட் பண்ணுங்க. ஓகே சார்.
ஜாய்சிந்தி உன் வீடியோ கட் ஆயிருக்கு
சார். நான் தான் கட் பண்ணிருக்கேன் சார். இருக்கட்டும்.
ஓகே
சார்.
Thursday 11 o'clock correct start பண்ணிரு.
Start பண்ணிரவா sir? Okay.
பண்ணிரு.
A very pleasant morning to all. With the blessings of Almighty, we start the session. Having your support, we, PG and Research Department of Physics, jointly with IKAC, the MDT Hindu College, Tirunelveli, completed the first day of the 2 days online workshop on research tools and techniques for material characterization. Now, we welcome you all for the second day of this online workshop. Now I request Dr. A.N. Sita Lakshmi, Assistant Professor, Department of Physics, to introduce the speaker of the day. Ma'am, please.
Thank you, Sandhya ma'am. It's a great pleasure for me to introduce the resource person of the day, Dr. E. Kumar, my friend and well-wisher, who is working as an assistant professor in Tamil Nadu Open University, Chennai. He also acted as assistant controller of examination in the same university and has 9 years of administrative experience. He has about 11 years of teaching experience, produced 2 PhDs and 4 MPhil scholars. 2 candidates submitted their PhD and 3 are enrolled. He has received Best Teachers Award from Tamil Nadu Open University on 2018. He has about 34 publications in reputed journals and he is a technical reviewer in 9 international journals. He delivered many guest lectures in various institutions and invited talks in national seminars. He is a member in different forums and also I am very happy to say that he is one of our notable alumni. With this brief introduction, I invite my friend Dr. E. Kumar to this 2-day online workshop on research tools and techniques for materials characterization. Hearty welcome, Kumar, please.
Welcome. Good morning. So, good morning to all. I am Dr. E. Kumar from Tamil Nadu Open University, Chennai. I would like to express my sincere thanks to my Honorable Vice Chancellor, Professor K. Parthasarathi, Tamil Nadu Open University, who permitted and encouraged me to take part in the workshop as a resource person. I would like to express my heartfelt thanks to my mentor and well-wisher, who, in Tamil, Mada, Pida, Guru, Devam. Mada, Pida, Guru. The moonu சேர்ந்து எனக்கு கிடைச்ச என்னோட குரு Dr. D. Mutharaj. He shaped me as an academician and he is such a great man who is behind my career success. I deem him next to God in my life. Good morning, sir. Thank you, sir. At the outset, I thank the principal, staff members of Department of Physics, the MDT Hindu College, Tirunelveli, for giving me an alumni of this great institution opportunity for delivering a topic on software tools and data interpretation of nanomaterial characterization. During this COVID-19 pandemic situation, all higher education institutions prefer to take an opportunity to interact with the students, researchers, and academicians by conducting the workshop through a virtual platform, so that the students and academicians can gain and upgrade the domain knowledge in their respective fields. It gives me a great pleasure to welcome you all at the forum, which would allow the participants, including students, researchers, and academicians, to familiarize with a current research and application in this area, and thus promote implementation of a nanomaterial with support of a sophisticated software and to make innovation with accordance to public needs. Now we start this session. The topic is software tools and data interpretation for nanomaterial characterization. So the outline is first the introduction of nanomaterial, then how to synthesize nanomaterial, then what are the material characterization, then what are the software tools used, then the data interpretation. So we know that the solid material can classify into 2 types, crystalline and amorphous. The crystalline material can further classify into 3 types: macrocrystal, microcrystal, and nanocrystal. So, what are nanomaterials or nanocrystals? The nanomaterial possesses a unique and interesting mechanical, optical, electrical, magnetic, thermal, and other properties. These materials range from inorganic to organic, crystalline to amorphous, which can be found as a single particles, aggregates, powders, nanowires, quantum dots, nanofilms, nanofibers, nanotubes, etc. So, what are nanoparticles? A nanoparticle is a microscopic particle whose size is measured in nanometers in 10 to the power minus 9 meter. The nanoparticles are a great scientific interest as they are effective bridge between bulk materials and atomic molecular structure. A bulk material should have a constant physical properties regardless of its size, but at the nanoscale, this is often not the case. The size-dependent properties are observed, such as the quantum dots in semiconductor particles, surface plasma resonance in some particles, and superparamagnetism in magnetic materials. These magnetic materials are classified into 4 types: a zero-dimensional nanomaterial, one-dimensional nanomaterial, two-dimensional nanomaterial, and bulk nanomaterial or three-dimensional nanomaterial. The example for the zero-dimensional nanomaterials are nanoparticles and quantum dots. The example for one-dimensional nanoparticles are nanowires, nanotubes, and nanoribbons. The example for two-dimensional nanomaterials are nanofilm and nanocoating. The bulk nanomaterial or three-dimensional nanomaterial, the example for this, the pellet form of a nanopowder and other nanostructured materials. Now, the semiconductor nanocrystals. The semiconductor nanocrystal are often referred as a quantum dots. These can be tuned to emit or observe a particular colors of light using solar energy or fluorescent or biological labs. In the nanometric range, metallic and small bonds in semiconducting material exhibit fascinating a quantum phenomena. A large bandgap material such as oxide stabilize in the temperature phase and exhibit enhanced surface phenomena like catalysts and reduce reaction barriers for solid reactions. So why we focus this nanomaterial? The specific properties is due to increase in surface area to volume ratio. Why we choose this nanomaterial? The specific or a significance of the nanomaterials are increase in surface area to volume ratio and the quantum confinement effect in the nanomaterials. The fundamental properties like decrease in the melting temperature, increasing in band gap, and blue shift in UV visible spectrum and change other properties are noticed. So the application of nanomaterials. The synthesized nanomaterial can be used for the fabrication of gas sensor devices, supercapacitor application, coating on solar cells to improve the efficiency of the solar cells, antibacterial activities, photocatalysts, and other nanotechnological devices. So here we explain the synthesis of nanomaterial. The general methods of synthesis of nanomaterial, there are 2 types of nanofabrication. One is top-down nanofabrication, another one is bottom-up nanofabrication. The top-down nanofabrication is nothing but the start with large material and it bring down to the nanoscale. The bottom-up nanofabrication is nothing but a start with the individual atom and build upwards to make a nanostructure. So this represents the bottom-up approach and top-down approach. Here, a molecular level to nuclei, then nanoparticles. So from bottom to top. The top to down, a bulk material into finally we get a molecular level. The example for the bottom-up approach are supercritical fluid system, Sol-Gel process, solvothermal method, microacid solution method, chemical vapor deposition, and so many methods. The top-down approach, a mechanical mining, etching, laser ablation, sputtering, PVD physical vapor deposition, and etc. Now, some of the nanocrystalline materials synthesized in our laboratory by me and my research scholars, some semiconductor nanomaterials and metal oxide nanomaterials. For example, CDS, ZNS, copper sulfide, manganese sulfide, zinc oxide. These are some of the semiconducting material. some rare earth metal oxides like cerium dioxide, titanium dioxide, tin oxide, zirconium oxide, and etc. And also we are synthesis a nano composites by using a polyaniline, one of the conducting polymer, a different type of polymer composite also synthesis. These materials have been prepared by a microwave solution method and in situ polymerization method. So now I discuss how to synthesis one of the nanoparticle by using a microwave solution method. So let us take CO2 nanoparticles. This is one of the very important and rare earth metal oxide nanoparticle. This material can synthesized by a microwave solution method. Let's take the precasting material, ammonium ferric nitrate and sodium hydroxide in the molecular ratio of 4:1. We take two different beakers with the certain amount of ammonium ferric nitrate and sodium hydroxide dissolved in deionized water. The sodium hydroxide solution added to the ammonium ferric nitrate solution dropwise and continuous stirring. Then the solution is kept in ordinary microwave oven. In our domestic microwave oven, we are using. So half an hour. First 5 hours, we switch on the condition. Next half an hour cooling. So repeat this process. After half an hour, we get a colloidal precipitate because the cerium dioxide is obtained a colloidal form. It's a colloidal precipitate washed with continuously deionized water and organic solvent acetone. Then after the washing, the materials are drying in ordinary air 1 or 2 days. Then it is subjected to annealing or at high temperature calcination process. After the process, we get finally a fine nano powders are obtained. Now we synthesize the nanomaterials. Then how to characterize these materials are really a nanoform or not? We check by using some characterization technique. Generally, the nanoparticles are characterized by a various technique: X-ray diffraction, UV visible spectroscopy, FTR spectroscopy, transmission electron microscope, scanning electron microscope, atomic force microscope, and etc. So in this topic, in this workshop, we interpret the powder XRD method and UV visible studies by using Argin and Excel. So first, what is powder XRD method? The powder X-ray diffraction method is one of the most important tool for the qualitative analysis of a material. The X-ray diffractometry is a non-destructive qualitative technique, the NDT technique, to investigate the crystal structure of solids. The information related to phase composition, grain size, internal lattice strain, preferred crystal orientation, lattice constant, unit cell, and degree of crystallinity of the material can be determined from the XRD results. It is based on the constructive interference of a monochromatic X-rays. So these are some XRD pattern. Now we enter this workshop session. Now we go to software. Now already we got the raw data from the X-ray diffraction. We got the X-ray diffraction pattern. Now we plot the graph. In x-axis is the diffraction angle. In y-axis, the intensity. So 2 theta y-axis the intensity. Now we plot a graph. So we get an XRD spectrum of this particular synthesized nanomaterial. Now we arrange the graph. So first we want to calculate the full width of maximum or size of the particles from this XRD pattern. Now we want to find the full width of maximum value by using the software. We go to analysis, the peak and baseline. We select the peaks and baseline. We choose a multiple peak, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So now we fix the peak. Now we fit this peak. So now we analyze and to find out the full width maximum value by using this. Now the peaks are fitted with the help of the software. Now the process is over. We get the 2 theta value and full width of maximum value from the software. So these are the 2 theta values. These are the 2 theta values. The corresponding full width of maximum value. These are the full width of maximum value. Now with the help of an Excel sheet, we are using this 2 theta value and full width of maximum value. We find out the crystallite size by using a Debye-Scherrer formula. So the determination of crystalline size of the nanomaterial. Actually, the powder XRD method, which is used to find or to investigate the crystal structure of solid and mainly to calculate the grain size. So these are some of the XRD pattern of nanomaterials. So first we determine the crystallite size of the nanoparticle using Debye-Scherrer equation. Then determination of crystalline size of the nanoparticle using WH method. Then structural analysis. So first determination of crystallite size, dislocation density, and microstrain. The average crystallite size can be calculated using a Debye-Scherrer formula. D is equal to 0.9 lambda by beta cos theta. Here lambda is a wavelength of an X-ray, that is 1.5406 nanometer. Where beta is a full width of maximum and theta is a diffraction angle. Now by using this relation to determine the crystal size of a particular XRD, so we get a 2 theta value as well as the full width of maximum value. Now these values used in one Excel file. So we choose the data of 2 theta and paste in Excel file. Then it is divided by 2, we get a theta value. The full width maximum value is calculated from the origin software. Now we get theta and full width maximum. The crystallite size, we have a formula, D is equal to 0.9 lambda. D is equal to 0.9 lambda, 0.9 into the value of lambda is 0.146, so 0.15406 nanometer divided by beta cos theta. Here beta is in terms of degrees. Now we want to convert in terms of radian. Here the full width of maximum value, that is C2 and cos theta. The theta also in terms of degrees, so it is converted into radian. Now the theta value is B2. Now the size of the particle is 26 point is. So by using this relation, we find out this particle size for each peak. We got around 12 peaks in the graph. We got a peak 1, peak 2, peak 3, 4, 5, 6, 7, 8, 9, 11, 12. These 12 full width of maximum values determined by using this. Then we find out the size of the particle by using Debye-Scherrer formula. The values are tabulated, the 2 theta value in terms of degrees. Then it is converted into degree, theta. Then full width of maximum in terms of degree. Now the convert degree into radian and degree into radian. Now we substitute the formula 0.9 lambda by beta cos theta. We get the crystallite size. The size of the particles are around 26 nanometers. The average size of the crystallite size of the particle is 26. Now, then to find the microstrain and dislocation density, another 2 structural parameters, microstrain and dislocation density, where dislocation density is 1 by d square, where d is a size of the nanoparticles. The microstrain epsilon is equal to beta by 4 tan theta, where beta is a full width of maximum, theta is a diffraction angle. So in the same Excel, already we got 2 theta value and full width of maximum value. And also we calculate the crystalline size by using Debye-Scherrer formula. So now we calculate the dislocation density, delta is equal to 1 by d square. We substitute the value for d is equal to the size of the nanoparticle, we get the dislocation density. Similarly, to calculate the microstrain, epsilon is equal to beta by 4 tan theta, where beta is the full width of maximum, theta is here. So by using this, we get the microstrain. So we tabulate the 2 theta value, full width maximum value from origin graph by using Debye-Scherrer equation to calculate the crystallite size. Then by using this to find the dislocation density and microstrain. Now the Debye-Scherrer formula or Debye-Scherrer equation is an approximate method. Now we want to calculate an accurate method. The accurate size of the crystal, nanocrystal, the accurate size of a crystalline of nanomaterial or crystalline size of the nanomaterial can calculated by WH plot method or Williamson-Hall plot method. So in XRD data, the broadening peak is due to the combined effect of crystallite size and microstrain. In XRD data, we got around 12 peaks. These peaks is broadening, some peaks are broadening, some peaks are a little broadening, some peaks are very high. So it is due to a combined effect of crystallite size and microstrain. So the total broadening is equal to broadening due to crystallite size plus broadening due to a microstrain. So we can write beta suffix t is equal to beta suffix d plus beta suffix epsilon, where beta suffix t is a total broadening, beta suffix d is a broadening due to crystallite size, beta suffix epsilon is a broadening due to a microstrain. We know the Debye-Scherrer equation, d is equal to 0.9 lambda by beta cos theta. Here lambda is a diffraction angle or Bragg angle, beta is a full width at half maximum, lambda is a wavelength of X-rays. Similarly, the XRD peak broadening due to a microstrain is given by beta suffix epsilon is equal to 4 epsilon tan theta. Now the value of 2 and 3 substitute in the first equation. The value of 2 and 3, beta suffix d and beta suffix e, substitute in this equation, we get the beta suffix t is equal to k lambda by d cos theta plus 4 epsilon tan theta. Now rearrange this, the tan theta can be written as sin by cos. Now multiply by cos theta on both sides, we get beta suffix t cos theta is equal to epsilon into 4 sin theta plus k lambda by d. This equation represents as a straight line in which epsilon is a gradient of the line and k lambda by d is a y-intercept. So we know that the equation for straight line is y is equal to mx plus c. So compare the equation 6 and 7, we get y is equal to beta suffix t cos theta, m is equal to epsilon, that is slope, x is equal to 4 sin theta, and c is equal to k lambda by d intercept. Now already by using a origin graph, we get the value of beta and the value of theta can calculated. Now by using this to find the value of y and x and plot between x and y, we find out the value of size of the particle or intercept and the slope or the microstrain. Now we go to origin. In the Excel file, already we get 2 theta value, full width of maximum, crystalline material, crystallite size, dislocation sensitivity, and microstrain. Now, the 2 theta value in terms of degree, it is converted into radian. The full width of maximum in terms of degree is converted into radian. Now we calculate the beta cos theta and 4 sin theta. The beta cos theta along y-axis, the 4 sin theta along x-axis. Now we copy this value. Go to the origin. Now we plot. So in x-axis, 4 sin theta. In x-axis, 4 sin theta. Now y-axis, y-axis beta suffix t cos theta. Now y-axis beta cos theta. So now we fit this line by using a linear fit, because the equation y is equal to mx plus c. We have the data. Now by using this origin software, we are fitting a linear fit. So now by using this, we got a line, a straight line fitting. Now the data are scattered. Now we rearrange the scale. Rearrange the scale. Now the data are very close to the straight line. So from the box we get the slope 144.216, then the intercept 0.96 this. So from this straight line fitting, we got the slope and intercept. So these values are used in a WH method to find the exact crystal size. So we draw the graph in between beta suffix t cos theta and 4 sin theta. We plot a straight line fitting. We get the y-intercept and the slope. So we plot a graph this, the value represents slope here, the y-intercept c is equal to k lambda by d. The c-intercept value is 0.00497. So the value, we know that c in terms of a nanometer, to substitute the value, we find out the crystallite size of this particular nanomaterial is 27.898 nanometer. This method is an accurate one. In a previous method, we calculate the crystallite size by using a Debye-Scherrer formula. It is approximate one, but in a WH method, it's accurate one. So very similar this. In a Debye-Scherrer formula, we get the nanoparticle, the size of the crystallites in terms of 26 nanometer. Here, the 27.89 nanometer. Then the microstrain, or the slope of the line, that is equal to 1.7626 into 10 to the power minus 3. So these are the characterization. So it's listed out here, the tablet 2 theta and theta. So next, so the first characterization technique, XRD technique. By using XRD, we find the crystallite size, dislocation density, microstrain. Then it is verified by a WH method also by using this origin software. Now, the UV visible spectroscopic studies, the calculation of band gap of nanomaterial from UV visible absorption spectra using a Tauc plot method. Now I am going to show you how to properly calculate the band gap of a nanomaterial from UV visible spectrum using a Tauc plot method. There are two types of band gap, direct band gap and indirect band gap. So first, what is direct band gap? The direct band gap is nothing but the top of the valence band and the bottom of the conduction band occur at the same value of momentum. In a direct band gap semiconducting material, the top of the valence band and the bottom of the conduction band occurs at the same value of momentum. It is also said in other words, in one which the maximum energy level of the valence band align with the minimum energy level at the conduction band with respect to momentum. The direct band gap is nothing but, direct band gap semiconducting material is nothing but the maximum energy level of the valence band align with the minimum energy level of the conduction band with respect to momentum. The indirect band gap semiconductor is nothing but the maximum energy of the valence band occurs at different value of momentum. to the minimum in the conduction band energy. In the indirect band gap semiconductor, the maximum energy of the valence band occurs at a different value of momentum to the minimum in the conduction band energy. It also, in other words, in an indirect band gap semiconductor, in one which the maximum energy level of the valence band and the minimum energy level in the conduction band are misaligned. In a direct band, they are aligned themselves. In an indirect band gap material, misaligned with respect to the momentum. Now, to calculate the direct band gap of a titanium dioxide nanomaterial. The titanium dioxide nanomaterial is an example for a direct band gap energy. The MnO2 nanoparticle is an example for indirect band gap energy. Now, how to calculate the energy band gap of a nanomaterial by using origin software or Tauc plot method. So normally we got the raw data from the characterization, the UV spectroscopic characterization. We get a raw data only wavelength and absorbance. Only we get wavelength and absorptions. Now, by using this value to plot first a UV visible spectroscopy spectrum. Now we calculate, first we calculate the UV visible spectroscopy spectrum. So before that, what is direct band gap and what is indirect band gap? In a Tauc relation, alpha h nu whole power 1 by r is equal to beta into h nu minus Eg. This is a Tauc plot relation. Here, where r is equal to 1 by 2 for direct allowed transition, r is equal to 2 for indirect allowed transition. For direct band gap material, r is equal to 1 by 2. So the equation 1 becomes alpha h nu the whole square is equal to beta into h nu minus Eg. So this equation is like a straight line. In left hand side is equal to 0. The energy gap is equal to h nu. Now we draw the graph between alpha h nu whole square versus the energy value. Now go to the origin. Already we have a raw data from UV visible characterization, the wavelength and absorptions. So now we plot a new graph versus wavelength versus absorptions. In x-axis, a wavelength in terms of nanometer. In y-axis, the absorptions value. Now we plot a graph between wavelength and absorptions. This is a UV visible absorption spectrum for the particular nanomaterial. Only the two absorptions are obtained for this. Now we want to calculate the direct energy band gap of this material. So we have the wavelength and absorptions value. Now we add more columns. First to calculate the energy value. We know that energy E is equal to h nu, or it is also called as hc by lambda. E is equal to h nu or hc by lambda. So here, this is a alpha h energy value. Sir, சொல்லுங்க சார். இல்ல போயிட்டு இருக்கு. So the energy is equal to energy in terms of electron volt. Now we directly calculate by using this origin program to calculate the energy, where E is equal to h nu or hc by lambda. Already we have a lambda. So h is a Planck's constant. The value of Planck's constant is 6.626 into 10 to the power minus 34 joules second. And c is a velocity of light. C is equal to 3 into 10 to the power 8 meter per second. So we simplify this, we get a 1240 electron by lambda electron volt. So 1240 by, we have a wavelength in column A. So we calculate the energy value in terms of electron volt. So next to calculate alpha h nu, where alpha is the absorption coefficient, that is 2.303 into the absorption value. So next we calculate alpha h nu the whole square. So from this equation, alpha is equal to 2.303 into absorptions. So column B into h nu, where already we calculate the h nu, the energy, this is column C. Then the whole square. Now we calculate alpha h nu and the energy value. Now we draw the graph between the energy versus the alpha h nu whole square. Sorry. So we get, this is the x-axis. First we said the axis is a x-axis. Now this is x and y. Now we plot. Now rearrange the expression, rearrange the graph. We change the value around 3.9. Now we get this a spectrum. Now by using a straight line fitting, this is a Tauc plot. We draw a line. We draw the tangent. Now this is the energy value in terms of electron volt. Here the value of alpha h nu square. Now the tangent of this line is so exactly a 3.14 something. So you draw the graph carefully. To fix that straight line or tangent of the line is carefully, we get the exact value. This is a direct band gap method. So first we draw the absorption graph, then a direct plot. So this direct band gap is exactly matched with the titanium dioxide nanoparticles. The direct band gap value is around 3.15. Actually the bulk nanomaterial is 3.2 electron volt. Here 3.15. So the direct band gap is directly calculated by using the origin program. Next to calculate indirect band gap. So what is indirect band gap semiconducting material? Direct band gap semiconducting material is nothing but the maximum energy level at the level of the valence band and the minimum energy level of the conduction band are misaligned with respect to the momentum. In a direct band gap, we get a fixed value, a 3.16 or 3.19 or 3.2, a fixed value. But in indirect band gap, the band gap value lies between because this is misaligned. So now to calculate the indirect band gap calculation. We know that the Tauc relation alpha h nu power 1 by r is equal to beta h nu minus Eg. E suffix G. We know that R is equal to 1 by 2 for direct allowed transition, R is equal to 2 for indirect allowed transition. We put R is equal to 2 this equation, we get alpha h nu whole power 1 by 2 is equal to beta h nu minus E suffix G. Here, alpha is the absorption coefficient, H is a Planck's constant, V is a frequency, beta is a constant, E suffix G is the energy band gap. By using Beer-Lambert law, alpha is equal to A by CL, where A is the absorption coefficient, A is the absorptions, C is the concentration of the sample, and L is the length of the cubic. By using Beer-Lambert law, the alpha can be written as alpha is equal to A by CL, where A is the absorptions, C and L are constant, C is the concentration of the sample, and L is the length of the cubic. Now this equation 1 shows like a straight line, so Y is equal to mx plus C. So in the left hand side is equal to 0, so E suffix G is equal to h nu. Then in left hand side, alpha h nu whole power 1 by 2, where here alpha is equal to A by CL, where C and L are constant, they do not change the nature of the curve. They just decide the magnitude of the peak along y-axis in the Tauc plot. In the left hand side, alpha h nu whole power 1 by 2, where alpha is equal to A by CL, where C and L are constant. They do not change the nature of the curve. They just decide the magnitude of the peak along in y-axis in the Tauc plot. So we neglect C and L. So alpha is equal to the absorption value A. So now to calculate the indirect band gap, now we get the UV data for the M102 nanoparticles, only wavelength and absorptions. We draw the UV visible spectroscopic graph by using origin. Now we draw the UV spectroscopic spectra for a M102 nanoparticles. In x-axis, wavelength in terms of nanometer. In y-axis, the absorption value. Now we plot a graph. So here the graph is entirely different. In previous one, a peak is obtained. Here, if two more absorptions are obtained, we rearrange the scale, we clearly shows. So there are two absorptions level are obtained in UV visible spectrum. So because these materials are indirect bandgap semiconducting material. So now to calculate the indirect bandgap for this material, we want to plot a graph between alpha h nu whole power 1 by 2 versus the energy value. Now we add more columns. First, initially we shed the column is x-axis. First, this is the energy. energy in terms of electron volt. We know that E is equal to h nu, where h nu is equal to c by lambda. So hc by lambda, hNc is a constant value. This is 1240 by lambda. So 1240 by the wavelength is in column A. So to calculate the energy value. Next, to calculate the alpha h nu whole power 1 by 2. Here alpha is the absorption coefficient. So alpha is equal to A by CL, where C and L are constant. So we neglect. So alpha is equal to A. So we write column B. This is the absorptions and the energy value. Column C and whole power 1 by 2. So now we get the value of E suffix G and value of alpha h nu whole power 1 by 2. Now we plot the graph between this. Now this is due to a misalign of the indirect band gap material. There are two tangents drawn here. This is due to some crystal defects. In indirect band gap semiconducting material, due to some crystal defect, we get a two slopes are obtained, a two energy band gap. So now we draw this. This is a one tangent. This is another one tangent. Now the energy band gap value lies between, this is a 3.04 electron volt to a 4.12 electron volt. So for M102 nanoparticle is the indirect band gap value. The band gap value varies between or lies between 3.1 to 4.2. The bulk material also, the energy band gap value is from 3 to 4.2. So this is one of the method to draw the indirect band gap value. So indirect band gap value is lies between this. So now this is a absorption spectrum. There are two absorptions are obtained within the range. The energy band gap value lies between this around 3 to 4.2. So now go to the summary. We discuss the classification of nanomaterial. 0-dimension nanomaterial, 1-dimension nanomaterial, 2-dimension nanomaterial, and bulk or 3-dimension nanomaterial. Then discuss how to synthesize a nanomaterial by using a microwave solution method. Then a different type of characterizations are there. We are choosing only in this workshop we are choosing powder XRD method and UV visible spectroscopic method. By using Origin and Excel software, the structural parameters of this nanoparticle, namely crystallite size, microstrain, dislocation density, and phase confirmation of the sample are calculated using the XRD technique. The Tauc plot were drawn from UV visible spectroscopic data, from which both direct and indirect band gap values of nanoparticles were determined. So thank you. This is for a questionnaire session.
Thank you, sir.
Thank you, madam.
Sir, it's a very clear explanation about nanomaterials and their characterization using software tools. No doubt you have given a very clear picture about powder XRD and UV characterization, which would really help the research scholars very much, sir. So,
Yes, madam.
thank you, sir. There are some questions in the chat box, sir. So, I kindly request you to clarify them.
Okay, ma'am, I will check.
Yes, okay, sir.
So one of the question from one person, in case of many samples, it is advised to calculate the average crystalline size or that for a highest peak. So actually, suppose we got more number of peaks, we don't take any one of two. My suggestion is to calculate the crystallite size by using Debye-Scherrer equation as well as WH method. We get one confirmation. Most of them are choose only any one of the broad and peak. So for example, I saw a graph. So in this graph, some people are taken only these 1, 2, 3. They are missing these peaks. So which reflect in the results. So by using a WH method, we get the exact value and compare with Debye-Scherrer formula. Then it is confirmed by a chart term. It is also reflected in FTR and some other studies. The same value is reflected in impedance studies also. So I suggest we take all the peaks. Then what indicates a negative value of strain in WH plot method? It is undoped Da2 indicates. So actually, we don't bother about the positive or negative value. This is only choose a magnitude. Y is equal to mx plus c or minus. Only we choose the magnitude only. You don't bother about the sign. So we use only the magnitude. This is a question from Selva Priya. Suppose you have any other question, please send through directly to my mail. My mail ID is kumarnano@gmail.com.
Okay, sir. We shall type it in the chat box, sir.
Yes, already.
Okay, sir. Shall we conclude, sir?
Okay, madam. Just a minute.
Yes, sir.
Okay, this is the time to conclude my session. I hope that the participant would gain the knowledge about the applications of selected software tools for nanometal characterization. Once again, I thank the authorities of the college, principal, and the organizing secretary, Dr. Joyce India, and my friend, Dr. Sita Lashmi, who introduced me in the session, and another my friend and my teacher, Dr. K. Balasubramanian, providing a wonderful opportunity to deliver this session. I thank the staff members and participants who are actively taking part in the webinar. I wish the participant to apply these software tools in their research and gain the knowledge in this domain. Thank you.
Thank you, sir. Thank you very much. Now, it's time to propose the vote of thanks. I am very much pleased to propose the vote of thanks. First and foremost, I thank the Almighty for the successful completion of this 2 days online workshop on research tools and techniques for materials characterization. At the outset, on behalf of PG and Research Department of Physics and IQAC, I convey my sincere thanks to Thiru M. Chellaya, Honorary Secretary, Thiru S. Meenakshi Sundaram, President, Thiru B.T. Chidambaram, Treasurer, elected members, Dr. R. Suresh, Thiru A.L.S. Sanmugam, Thiru D.R. Thirumalayappan for their constant support and encouragement. I would like to thank the resource persons, Dr. R. Ganapati Raman and Dr. E. Kumar for their immediate acceptance for our invitation among their busy schedule. Once again, I thank them for their concern and wonderful presentations. I thank Dr. A. Subramanian, Principal, for his encouragement and support. I thank Dr. K. Balasubramanian, Coordinator, IQAC, for his guidance and moral support. I thank Dr. D. Mutturaj, convener of the program, for his kind support. I extend my thanks to organizing committee members, Mrs. D. Guruammal, Dr. J. Uma Mageshwari, Dr. A. N. Sita Lakshmi, Mr. N. Arumugasamy, Dr. D. Silambarasan, and Mr. R. Subhash Chandra Bose for their backing support. I extend my thanks to all the participants from various institutions for your cooperation. My special thanks to Mr. Subhash Chandra Bose, Assistant Professor of Physics, for the technical support. The beautiful thing about learning is nobody can take it away from you. With this note, we conclude the event. Participants kindly submit the feedback link before 2 p.m. E-certificate will be issued within a week to only those who submit the feedback form. Thank you one and all.
Madam, I have one question. May I ask you?
Ask.
Sir?
Sir, this is Sudhir from the Sambalpur University, Odisha. May I ask you one question?
Okay.
Sir, first of all, I thank you because your session was really wonderful. It was quite helpful for our research. So I wanted to have the PPT because there are a lot of things to learn. So if I get the PPT, it will be easy for me. If I, sometimes in the future, if I get some doubts, I can look at the PPT, I can learn something.
I will share.
So is it possible? Thank you, sir.
Okay, thanks. Okay, thank you.
Bye, sir. Thank you, sir. Thank you very much.
Thank you, thank you.
Subhash sir.
Sir, சொல்லுங்க sir.
Silambarasan sir.
இல்ல மேம் நான் சுபாஷ் சார் கேட்டேன்.
ஓகே சார், ஓகே சார்.
ஓகே மேம் ஒரு 5 மினிட்ஸ் கழிச்சு க்ளோஸ் பண்ணலாம். அது ஃபீட்பேக் அவங்க காப்பி பண்ணி கொடுக்கணும்.
ஓகே சார், ஓகே சார். குமார் சார், பிரசன்டேஷன் ரொம்ப நல்லா இருந்துச்சு சார். ரொம்ப ஸ்மூத்தா போச்சு. Thank you very much சார்.
Thank you madam.
Thank you சார். எந்த டிஸ்டர்பன்ஸும் இல்ல சார். ரொம்ப கிளியரா, ரொம்ப எப்படி சொல்றது, நல்ல ஸ்மூத்தா கொண்டு போனீங்க சார். லைவ்லியா இருந்தது சார். ரொம்ப நல்லா இருந்தது சார். Thank you சார்.
ஓகே ஓகே, thank you madam. Thanks சார் தான் மேடம் சொல்லணும்.
ஓகே சார், சொல்லிடுறேன் சார். இப்போ உடனே அடிச்சு சொல்லணும்.
ஓகே ஓகே மேடம்.
ஓகே சார், ஓகே சார்.
மா thank you so much. சூப்பரா இருந்தது.
எல்லாம் உங்களோட இல்லதான்.
நல்லா இருந்தது உண்மையிலேயே.
Thank you சீதாலட்சுமி மேம்.
ஆஹா, எதுக்கு? ரொம்ப நல்லா இருந்துச்சு. ரொம்ப இன்ஃபர்மேட்டிவ். நிறைய பாத்துட்டீங்களே, சாட் பாக்ஸ்ல நல்ல ஃபீட்பேக் வந்துட்டே இருந்தது.
நான் பார்க்கல.
நிறைய ஃபீட்பேக்ஸ் இருக்குது.
ஃபீட்பேக்ஸ் ஆமா நிறைய இன்ஃபர்மேட்டிவா இருக்கு. சோ ஸ்டூடண்ட்ஸ் இதுதானே விரும்புவாங்க. ரொம்ப நல்லா இருக்கு.
நான் இன்னொருத்தவங்க கூட கேன் யூ ஆர்கனைஸ் தி சேம் ஒன் அகைன் சார் வெரி சூப்பர் அப்படின்னு அனுப்பியிருக்காங்க.
யார் மேடம்?
Credit goes to organizing secretary.
இல்ல அப்படியெல்லாம் இல்ல, சும்மா இருங்க மேடம். ஹரிராஜன் சார் ஃப்ரம் ஹரிராஜன் அப்படின்னு போட்டிருக்குது சார்.
குருமால் மேம் இருக்கீங்களா?
மேம் இருக்கிறாங்க மேம்.
குமார் சார் சூப்பரா இருந்துச்சு சார்.
குமார் சார் வந்து மியூட் போட்டுருக்காங்கன்னு நினைக்கிறேன்.
ஹலோ மேடம்.
குமார் சார் நல்லா இருந்துச்சு சார். ஆரிஜின் எல்லாம் சூப்பரா எடுத்தீங்க சார்.
थैंक यू மேடம்.
ஆமா சூப்பரா இருந்துச்சு சார். எக்ஸ்பிளனேஷன் எல்லாமே சூப்பர். ஏகப்பட்ட क्वेश्चंस நினைக்கிறேன். ஏகப்பட்ட क्वेश्चंस.
ஓகே மெயிலுக்கு அனுப்ப சொல்லுங்க மேடம். பார்த்துட்டு ரிப்ளை பண்ணிக்கிறேன்.
சரி சார். நல்லா இருந்துச்சு சார். நல்லா இருந்துச்சு.
மெயிலுக்கு அனுப்பிடுங்க.
ஓகே சார்.
நான் மெயில் ஐடி இருந்துச்சுன்னா உங்களுக்கு நான் ரிப்ளை பண்ணிடுறேன் மேடம். ஒன்றும் பிரச்சனை இல்லை.
ஹலோ சிந்தியா மேம்.
மேம் தேங்க்யூ மேம்.
ஆமா
எல்லா கிரெடிட் டு டிஎம் சாருக்கும் குமார் சாருக்கும் சீதாலட்சுமி மேம்க்கும் மேம்.
சரி எல்லாருக்கும் இன்னும் தேங்க்ஸ் சொல்லுங்க. அவ்வளவுதான். தேங்க்ஸ் மேடம். சூப்பர்.
ஓகே தேங்க்யூ மேடம்.
குமார் எங்க யுனிவர்சிட்டியா?
இல்ல வீட்ல.
ஓகே. இன்னைக்கு லீவ் தானே? என்ன
இன்னைக்கு லீவ் தான். இன்னைக்கு ஈவினிங் தான் கார் டெலிவரி எடுக்கணும்.
சரி. ஓ சூப்பர். கங்க்ராச்சுலேஷன்ஸ்.
ஓகே thank you.
கங்க்ராச்சுலேஷன்ஸ் சார்.
thank you மேடம்.
என்ன காரு?
Hyundai Creta.
சரி.
சிலம்பரசன் சார் தேங்க்யூ சார்.
மேம் தேங்க்யூ மேம். மேம் முடிச்சிடலாமா?
சுபாஷ் சார் இருக்கிறாங்களா?
சுபாஷ் சார்ட்ட நான் பேசுறேன் மேம்.
சார் ஹரிராஜன் இருந்து உங்களுக்கு மறுபடி ஃபீட்பேக் வந்துட்டே இருக்கு சார். கண்டக்ட் குமார் சார் அகைன் அப்படினா கிளாஸ் வெரி நைஸ்.
ஓகே
ப்ளீஸ் வி வாண்ட் அகைன் அப்படின்னு சொல்லிட்டு அவர் மெயில் ஐடி எல்லாம் போட்டிருக்காப்ல.
கொஞ்சம் கால் பண்ணி எனக்கு அனுப்பிடுங்க மேடம்.
சரிங்க சார்.
அவங்களுக்கு வேணா திரும்ப பிபிடி ஷேர் பண்ணிக்கலாம். வேற எதுனா கூட இன்னொரு வாட்டி கூட வேற என்ன கொஞ்சம் கேரக்டரைசேஷன் பண்ணலாம் மேடம்.
பண்ணலாம் சார். ரொம்ப கிளியரா இருந்துச்சு சார்.
இதே கம்மியா தான். நான் எனக்கு இது என்னன்னு தெரியல. இன்னும் கொஞ்சம் நிறைய பண்ணலாம் இதுலயே. அப்புறம் இன்னும் 2 சாஃப்ட்வேர் இருக்கு. ஆனா அது எல்லாருக்கும் இந்த சாஃப்ட்வேர் அவைலபிளா இருக்கா